Hi, and welcome to this hands-on introduction to FAIR ML pipelines. The links to this presentation and the GitHub repo for the workshop are available in the chat channel, and will also be provided again during this presentation, so that you may follow along if you wish to. During this workshop, we will have first a presentation where we will go into the details of fairness. What does it mean? How can you measure it? And why it is important to include it in your machine learning pipelines. After the presentation, you will get the chance to use your newly acquired knowledge, solving practical problems in Colab, which is Google's managed Jupyter Notebook environment. The notebook exercises can also be run on-premise if you wish to set up the environment yourself. And more instructions are provided in the GitHub repo for the workshop. I want to first introduce you to my co-speaker, Josephine. Josephine, can you introduce yourself to our viewers?
Yes, thank you, Marco. Hello, I'm Josephine, and I'm a system developer in Computas, and I'm working in our data science department. And I'm working with machine learning and with search, and then I'm working with responsible AI as well. And then I did my master thesis on how to measure fairness in recommendation systems. But that's not going to be the theme today. Today we're going to talk more about fairness in classification.
Thank you, Josephine. Before we go on, I'll tell also a bit about myself. I'm a mathematician working as a software engineer in Computas for about 10 years. I work now in technical pre-sales, where I'm responsible for machine learning, especially in responsible AI, and search as in information retrieval. And I also lead our research cooperation with the University of Oslo series within Explainable AI. So the agenda for this talk is as follows. First, we will discuss what trustworthy AI means, or as many others call it, responsible AI. Then we will go into how to operationalize fairness and go deep into some fairness definitions and some example architectures where you can introduce fairness into your machine learning pipelines. And lastly, we will touch upon transparency and interpretability. And after that, you will get a short break to start to work on the workshop tasks by your own. And then we will come back and review some of the notebooks together. We will also be available for questions in the chat room for the whole time during this workshop. Our first point is that machine learning is a process. It's not a tool. And here's an overview of the typical tasks you have to perform when building a machine learning pipeline. This is based on a paper done by Google, where they tried to quantify how much of the code that you are using to develop a machine learning model has to do with, in the machine learning pipeline, has to do with the model. And that's just about 5% of the code. So the other bits of what you have to do in a machine learning pipeline is go to data collection, data management, exploration analysis tools, model training at scales, and of course, best practice for monitoring, automation, logging management, feature engineering, and serving the models. Machine learning is different than usual software development. An analogy here is to think of traditional software development as being one-dimensional, where you have to care much about the code and the life cycle of the code. But machine learning is three-dimensional, because apart from the code, you also have to care about data and the model. And here you have to be able to track the changes in all these dimensions. And you have way more feedback loops, and you need multidisciplinary cooperation to make things work. You need to care about data lineage, where things come from, about provenance, model governance, model and feature drift, and so on. So apart from that, to introduce ML in your organization also demands a change in culture, similar to the DevOps mindset. You need to react quickly and embrace change. Since all this depends on data, you also have to think about how to build these systems in a responsible and ethical way. So, for aid, to help us with this challenge, we can refer to the ethics guidelines for trustworthy AI from the European Commission, where they decompose trustworthy AI into 7 overlapping subjects. As you see, the relationship between these subjects can be quite complex. It's not that you can separate these issues by themselves. So our focus today will be on diversity, non-discrimination, and fairness, primarily. But we also will touch upon transparency and technical robustness. And here, transparency demands that both technical and human decisions can be understood and traced. Non-compliance with transparency opens up for the creators of the algorithms to provide incomplete or misleading descriptions about how their models work, about how the data has been collected and pre-processed, and various other kinds of errors that can easily go unnoticed. So diversity, non-discrimination, and fairness are requirements that ensure that the AI system is accessible to everyone. And these include, for example, bias avoidance, or the consideration of universal design principles, and the avoidance of one-size-fits-all approach. You can read more about all these other areas in the link below diagram. So what does it mean to work with fairness in practice? Well, first of all, you have to be able to define what you mean by fairness in your context. When you have done that, you have to operationalize the definition in a quantitative and measurable way by using metrics and evaluating the results of this. And lastly, you integrate these metrics into the optimization process. By far, the most challenging part of the process is the first step. Fairness is context dependent. There are several definitions, and finding the best way to go from your moral principles of fairness to the correct metric implementation is really a huge multidisciplinary and multi-stakeholder process. Fortunately, we have here, let's assume that you have done the first step. We will not go into so many details on the first step. There are nice frameworks that can help you find out what are the right questions to ask to get to this. But let's say that you have already your definition of fairness. How do you go on then? Here we present you with 3 open source libraries from the biggest actors in the market. The first one is IEF 360. This has been around for some time, and it seems to us that this is the framework preferred by the fairness, accountability, and transparency community in machine learning. They have a great number of metrics supported for both detection and mitigation, and the framework is easily extensible and have great documentation and a web demo that Josephine will show us a bit afterwards. The second one, FairLearn from Microsoft, this is a recent contestant. They support also regression, and as far as I know, I haven't seen any other libraries supporting regression in fairness. This is also integrated within the Azure ML platform, and it comes with a nice dashboard to explore the metrics and mitigations. So it scores very high in usability. The third one is Fairness Indicators from Google. And this is a library that integrates very well with TensorFlow, if that's what you're working with. At the moment, they support only detection, and you can use the what if tool to explore different metrics. They also release another library called TensorFlow constraint optimizations, where you can add fairness constraints into the model optimization part. So these two tools can be combined to deliver fairness in TensorFlow, for example. To be fair, there are also more open source libraries, but these here seem to be under active development and backed by the biggest actors in the market, which guarantees the continuous development and improvement of the libraries. I totally disregarded fairness in recommendation systems, which is one of the Josephine's areas of expertise. But this is a bit more complex than the usual problem of classification, and we can leave this to a future talk. In this workshop, we will focus mainly on IS 360 because of the rich amount of techniques available and the great resources available on their documentation. So for now, let's continue with a deep dive into fairness with Josephine.
Thank you, Marco. So let's look a bit more on, first of all, how to define fairness, and then including how to measure it, and a little bit on where and how we can mitigate it. So first of all, when trying to understand fairness definitions in machine learning, we first need to understand the distinction between what we call group fairness and what we call individual fairness. Individual fairness means that similar individuals should receive similar results. Intuitively, this is pretty simple to understand, but it's a bit more difficult to actually measure in practice. Group fairness means that different groups, rather than individuals, should receive similar treatment or outcomes. And group fairness is some of what it seems to have taken up most effort in the literature, and group fairness is also what we're going to focus on today. Okay, but before we move on, let's get some important words and notation right. Because first of all, what we will consider today is fairness in classification. And in classification, the aim is to be able to correctly classify a label Y. When considering group fairness, again, we distinguish groups by a variable we name the sensitive or the protected variable. This could be race or gender or ethnicity or whatever. And often we denote one group as the protected or the privileged group, and the other group as the non-protected or the non-privileged group. Okay, so let's first consider one type of fairness definition that is concerned with equality of the representation with respect to the predicted label. Or in formal math, this definition of statistical parity tells us that we want equality, or we want that the probability of a given outcome Y should be the same no matter if you belong to the privileged or the unprivileged group. Let's try to understand what that means with a real life example. So Google's online advertisement system have been criticized because a study has shown that male job seekers are shown high-paying executive jobs significantly more often than female users. So in this case, the definition of statistical parity does not hold true, as we see a significant difference in the results between men and women. In order to comply with statistical parity, the probability of being exposed to a job advertisement of a high-paid executive job must be the same for both groups. So that means that if 20% of all male are exposed to a specific high-paid job, then also 20% of all women should be exposed to the same ad. And this is also despite any actual differences in labels or features across these groups. This type of fairness definitions thus reflects kind of the idea behind quota systems, or a situation where you wish to enforce a change in the future rather than reproducing the past or the present as it is. Okay, so far we have considered statistical parity a constraint, but to make it into a more measurable metric, we can either consider the ratio of the probabilities or the difference of the probabilities in order to be able to optimize for these measures and evaluate them. Okay, a different group of fairness metrics, they relate to equality in terms of accuracy and errors rather than equality in terms of the output labels. So basically the assumption behind these kind of definitions is that we want to be equally good or equally bad at classifying one group compared to the other. But often we do not only care about making equally few mistakes, we also want to make sure that the type of mistakes we make is not unfairly distributed. So one measure that is often used is called equality of odds, and it's a metric that evaluates if both the false positive rate and the true positive rates are equal. So this metric is useful when false positives and true positives are equally harmful, or false positives and false negatives are equally harmful. And be aware here that the true positive rate is the inverse of the false negative rate, and therefore true positive rate is the true positive rate of this metric could have been exchanged with the false negative rate. And then as you see, it's the two error types that we are measuring. We're measuring the difference in the false positive rate and add that with the difference in the false negative rate and take the average of that. But in some cases, we do not care about equality in terms of errors in both directions. Sometimes one direction is enough, and in that case, we can use equal opportunity as a metric instead that only considers the true positive rate. And to give you an example of that, if we consider the case from before with the job advertisement, it can be argued that the false negatives, meaning those who are not being exposed to a job ad that they are actually very interested in, is their dream job, that's more harmful than being exposed to a job that you're not really interested in, that doesn't really harm you in any way. So in that case, considering only equality with respect to the false negative or the true positive rate might be enough. Okay, so let's try to understand this metric in a different way, or with the real-world example. So one example that is often mentioned when we are discussing fairness in machine learning is the so-called Confer score. The Confer score is based on an algorithm, and it is used to estimate the risk of recidivism for inmates in the US. But the Confer score has been evaluated and very much criticized for being biased against Afro-Americans, because it has shown to systematically overestimate the risk score of Afro-Americans, while it systematically underestimate the risk score of ethnic whites. So this violates the definition of equal odds that we just discussed, because the false positive and the false negative rates are very different depending on ethnicity. The company behind the Confer score, however, they claim that the algorithm is actually fair, but with respect to a different metric that evaluates equality in the positive and negative predictive value instead. So these two different definitions of fairness stem from different metrics in the classic confusion matrix. And it's important to be aware that these two metrics often, in most cases, are not possible to achieve at the same time. So you have to make a trade-off between these two definitions when the base rates between the two groups are not equal. So these different definitions, they easily get a bit confusing, and which one is most fair is always debatable, and it always depends on the context, of course, also. So what is fair? A fair result is not always just easy to agree on. However, this institution called Equitas, they have made this very nice decision tree to help us guide the decision on which definition of fairness do we even want to apply in our context. And as we discussed, first, there is this distinction between whether you consider fairness in terms of representation, if you want to apply measures such as statistical parity, or if you want to measure fairness in terms of errors. And in case you want to measure fairness in terms of errors, then you have to decide on a metric, based on whether your interventions are punitive or excessive, and whether you're intervening with a very small percentage of the population or not. And this is just a smaller subset of the tree. If you go to this link, you will see an even richer decision tree. And Equitas have some very good ways of explaining these metrics as well. So I can very much recommend that. All right, another thing I just very briefly want to introduce is this resource, which is a very great visualization of some of the metrics that we have just discussed. It is a simulation of loan decision for different groups based on different thresholds. And it gives you a very nice overview of what are the trade-offs between some of these metrics. All right, so now we have kind of tried to get an understanding of what kind of different fairness definitions exists, and now let's see how to or where to evaluate these metrics and how to try to mitigate any potential bias that we might find. First of all, bias can exist and thus also be mitigated at different stages in the machine learning pipeline. And bias can often exist or be inherited already from our original dataset or our training dataset. And in case that we have bias in our training data, this bias will most likely be picked up and be reproduced or picked up by the model and be reproduced into our results. So in this case, we can attempt to mitigate the bias by doing some pre-processing of the data before we even start training our model. So this might be changing the labels or changing the representation of groups in our dataset. Bias can also be introduced or be enhanced by the model itself. So as an example, if our model is totally naive and the model uses only gender as a variable for any decision, and thus it assigns all women one label and all men a different label. In that case, our input data can be totally balanced, but the results could still be unfair. And in this case, we can only detect bias in our results, not in our input data. And we can only mitigate bias by enforcing a fair result through constraints in the algorithm. And we call this attempts to do in-processing optimization or fairness mitigation. Finally, our data could be fair, and the model we use seems to ensure a fair result when applied to our test data. But when applied to our training data, but then when we apply it to our test data or to our real-world data, result gets unfair anyway due to some imbalance in the test data. And in such case, we can choose to do some post-processing of the initial results that we receive to enforce a fair result in the end. When it comes to evaluation of bias, we also, of course, have to be aware that we can do evaluation of our training data or our original data only if the metrics that we want to evaluate is statistical parity or other metrics that are related to the classification label, because that's the only the only values that are known in the before we start training the model. The other error-based metrics, of course, we need to do the processing and get some results before we can start doing any fairness evaluations. What I just discussed here is described in a bit more complicated pipeline that you can take a look at. It gives a very good overview of the different algorithms and when to evaluate the different metrics. But basically, this just showed what I just discussed before. Marco, can you tell us a little bit about how this relates to transparency and interpretability?
Yes, thank you, Josephine. That was a great introduction. It's important to know that when you are working in high-stakes domains like healthcare or justice, or when you are taking decisions with the machine learning system that have potentially critical consequences for someone, it's really important that you can use fairness to try to evaluate the possible consequences of your decisions. There is an ongoing debate in the community about explainability versus interpretability. So many use these two terms as interchangeable, but they are really not. Explainability refers to the possibility to explain how the model you train makes decisions, try to explain the internals. You usually take a black box model, and what you do is, like, since you cannot look into the black box, you create a proxy that is going to be an approximation. This will be something you call explanations. And this is what you use to present to the users, to us, or to the developers as why the model is working like that. The problem with that approach is that you are highly dependent on your proxy and how well it reflects your black model. And the more it closes, if you want to approximate your black box model more and more, you end up having the black box model, right? Or if you end up having something that you can use instead of your black box model. Interpretability aims to build glass box models, which are transparent in the sense that you understand the inner workings and how the model makes decisions. An example of this are decision rules or a decision tree, where you can follow the workflow. These kind of models don't really need this proxy. So if you have the time, take a look at this talk from Cynthia Rubin, where she's one of the strongest proponents of interpretability, where she discusses mainly why you should aim to build interpretable models. And she also discusses there is the trade-off between accuracy versus interpretability, because many mean that having interpretable models, they won't be as accurate as your black box models, and that's not necessarily true. So she has come with theoretical tools on how to evaluate when really good interpretable models it's possible to find them. The other thing we want to say is that transparency really must preclude fairness, because you cannot audit what you cannot see. And being transparent makes it possible to scrutinize the methodology taken and the calculations of your model. So if we want to compare these glass box models versus these black box models, the glass box models are easier to inspect and understand. They are easier to explain, but of course there is a but. They are more difficult to build in the sense that they require more domain knowledge, or the optimization problem you're trying to solve becomes really hard, like NP hard. But at the same time, if you find an issue with your model, that, for example, your model is using race when it shouldn't use it, it's much easier to fix than your black box model. And this is like my particular view, maybe. For example, the post-processing algorithms that Josephine was discussing is something that you do if you can't change your model. But it makes your pipeline much more complex, and it's a bit harder to maintain on the long run. Because fairness is also something that you just not evaluate just once and you're done with it. It's something that changes over time. Here in this slide, you will see some examples of other techniques, of interpretable techniques, like explainable boosting machines, or SLIM, and the ProtoPNet. This is an attempt to make neural networks more interpretable, where this is a nice paper where they try to classify birds, and the paper is called "This Looks Like That." So what you do is that you look at pieces of the image and try to find prototypes in your examples. And then when you're going to classify a new image, then what you do is like you try to score these pieces of images to the prototypes and take the overall score. So you can always see how the network is thinking and building the score to classify the birds. So this is another approach. And the problem with black box methods is that, of course, they are harder to inspect and understand and to explain, but they're really easy to build. I mean, neural networks now, you don't really have to think that much about your data. You just can put it into your algorithm and something will come out. But when you get something out, it will be harder to fix, harder to understand when these things are taking wrong decisions. Yes. So then what we will continue now is Josephine will go now and show you the web demo from IBM 360.
Yes, and now it's almost your turn to start getting some hands-on experience with some of these fairness metrics yourself and how to do fairness or include fairness mitigation in your pipelines. But before that, I just want to introduce you a little bit to this AIF 360 library that we will invite you to start working on yourself in a moment. So if you go to this link, the community behind the AIF 360 have not only just created a library or a Python package, they have also created this very nice introductory web page where you can try a web demo and where you have a lot of resources available. First of all, here we got a link to the GitHub repo where you can go and install the package yourself if you want to continue working with this remotely. And there's a nice description on how to install everything on your computer. Then they also have a link to their API documentation. And what comes with this library is already some predefined or pre-installed dataset that you can get started with straight away. So we see 4 standard classification datasets here, which are available to start training on. Apart from these datasets, we also have all these fairness metrics. And we can see here as an example, we have the binary labeled dataset, which means this dataset that is concerned about equality or statistical parity and other metrics concerned about how to evaluate fairness in terms of the the labels. And if we take an example here, we got statistical parity difference. It's an alias of the mean difference. And in here, we also got a reference to a paper where we can read more about this metric, and we get a small idea of or definitions of what this metric actually means. Apart from that, there's also a collection of algorithms that we can play with in order to try to mitigate any bias that we might find in our data sets. And as you see, we have pre-processing algorithms, some in-processing, and some post-processing algorithms already available. Yes. What else? There is some tutorials, some papers. There is reference to the Slack channel, where my experience is that it's very easy to get help if you get stuck somewhere. And then there's these notebooks that we're going to take a look at in a second. And then they also have this nice web demo where we can get an idea of what kind of job this library can help us do. So first of all, we can choose a dataset that we want to evaluate. Let's go with this German credit scoring, because that is the first dataset that you have to work with in a minute. Oh, and if we go back for a second, what we see here is that the German credit scoring dataset is used to predict an individual's credit risk. And we can choose different attributes as the protected attributes. We can both do the evaluation based on sex and based on age. And then we have male and female, old and young as the different groups. So let's perform the evaluation. So what we see here is the evaluation of fairness with respect to some of these different metrics that we have touched upon today. And we see that for gender as the protected attribute, we see that it's actually pretty fair, this dataset already. The statistical parity difference is pretty close to 0. And if we don't remember exactly what statistical parity difference means, there's a nice help here, including a note on what should the ideal value be. There should be 0. And fairness for this metric should be somewhere between 0.1 and minus 0.1, which we also see is the case. The same for equal opportunity. And then we have disparate impact, which was again the ratio between the probabilities. Okay, let's consider age as the protected attribute, and here we see that it's actually there exists some bias, some unfairness for young people compared to older people. And again, we can get these explanations, and we can see that both disparate impact and equal opportunity is not being respected in these cases. So let's go next and see what we can do to mitigate this. We got the opportunity to choose between 4 different algorithms here, and we can see that we can choose to try to mitigate this unfairness with some pre-processing algorithms, one in-process algorithm, and one post-processing algorithm. So let's try to go with this adversarial debiasing, which is an in-process classifier that tries to balance the aim of accuracy while reducing an adversary's ability to determine the protected attribute from the prediction. So that means balancing accuracy with the aim for fairness. Let's go next and see what happens when we try to mitigate using this algorithm. Okay, so the gray results here are the original results, and now we see also some blue results, which are the mitigated results. And what we see here for the attribute gender is actually that the results turn out to give us even more unfair results than before. So we went from an almost perfectly well-balanced, fair classifier to now a somehow more unfair result. So in this case, this algorithm apparently didn't help us a lot. But let's see what happened for the age attribute. Here we saw some unfairness before, and we see that we have very much reduced the statistical parity difference, improved the disparate impact that we want to be close to 1, and also for equal opportunity difference, we have got closer to obtaining a fair result. Yes, I think that was it for this web demo. If we go back to home, then we also have this link for some notebooks. But to make things easier for you to work with, Marco and we have worked a bit on these notebooks and put them into Colab so that you don't have to consider anything with any environments and downloading the package yourself. These notebooks should be ready to run, and you can find them using this link that we will also post on Slack, bit.ly/fairml workshop. And in here you find the link for these Colab notebooks. If you're not familiar with Colab, basically this just runs like standard Jupyter notebooks, but you don't have to set up any environment. This should be totally automated. So take your time now, go through these notebooks, start from the top, and try to get an idea of how this code works in practice. And then at the bottom of each, there's also a lot of description. Most of this is directly copied from the AIF 360 notebooks, but we have also added a little bit of exercises and questions for you to not only just reproduce this, but to have to interact a little bit with the code yourself. So I think you will have 15 to 20 minutes now, and then we will go through these notebooks and the exercises afterwards.
Welcome back. What we're going to do now is go through the first notebook of the workshop. So hopefully you have seen the GitHub repo for the workshop. And here we have the first notebook that we're going to go through, which comes, if you click on this link, you will come directly to the Colab instance. I'm just going to increase my font a little bit so that it's easier to read. Yes. So this is the first notebook for our tutorial on fair machine learning pipelines. And this notebook is an adaptation of the tutorial for credit scoring from the IEF 360 repo. So if you click on this link, you will get to the original notebook. We have made some modifications so that you can run this notebook in Colab. But if you want to run this in your own environment, it's recommended that you follow the instructions in this link to install your virtual environment, for example. One thing you have to do is to check that you are, yes, when you start, this notebook was not out by Google, so you just say run anyway. We have to make sure that we have Python 3. Yeah, when we were making this, Python 2 was still available, but now it's not. So probably this is easy because this is the default setting. And then we have to install IEF 360. And you see lots of other libraries which are taken from the requirement file from the IEF 360 repo. There is a link to that file a bit later on. If you try this by yourself in maybe a month or two, because you want to try this notebook again, it will probably change because Colab also changes. So if you have some issues there, you just have to remove these versions and then see what kind of inconsistency with the packages you get, and then you just put the correct version and things will work. But at the moment, this works. So we install the right dependencies. There are some other dependencies that we have commented out that we don't need for this actual notebook. So, but you will need them in the next notebooks, in the next exercises. At the same time, we provide pip freeze will tell us all the versions of the libraries that we're using. In case you're having issues, you can come back to the repo because this is committed, and then you will see which libraries are compatible with this. Before we go on, there is an issue also with pandas. Pandas is now in version 103 at the current time, and the implementation of the standard dataset in IEF 360, this library is the one that loads the standard datasets. This has a reference to a function that is no longer implemented in pandas 1. So if you use pandas with a version previous to 1.0.100, you will get an error. And that's why we have to patch at the moment IEF 360. And it's not very difficult. It's just changing pandas series into a NumPy array. And this cell here, if you run this cell, it will overwrite the right file in the right place, as long as you still have Python 3.6 in your runtime. If you want to see what the code does, you can click here and form and show code. I just have copied the file and fixed the problem, and then you just run it. There is also another issue with Colab that it needs Markdown display to show nice prints of the results, and this is not available in Colab. So we made our own print function. We just write in boldface doing this. So this is one of the changes also we did in the notebook. This is the link to the requirement files that I was talking about. So we run the cell, Control Enter, we'll run the cell, or you can just click on play. And what you get now is the start of the real notebook from IEF 360. And you get an introduction to biases and machine learning that you can read, and a little bit about the dataset. So hopefully you have read the whole instruction, and many of these things we just recently covered in the presentation, like the machine learning workflow. Then you come to the part where you choose the dataset you're going to work with, and this is going to be the German credit dataset. I have also added some links to the raw dataset documentation in case you want to look at the details of the dataset. And here you get where the link where the dataset was collected from. And here is also a little more information if you want to read about that. And the code, documentation code, which is the class and how this is implemented in ABM. So what we're going to do is that this dataset has a variable called H. It's a loan dataset where people with German banks wants to loan money to their citizens, to their users. And we are going to work with the protected attribute H, where we're going to define that people with an H over 25 or equal to 25 will be in the privileged group, and people with an H lower than 25 with the unprivileged group. So we want to see if there is a fairness for young people versus the rest. And what we're going to do in this notebook is just to check for bias in the initial training data, mitigate the bias, and recheck again. There is a possibility to do a more sophisticated workflow, but you will see that later also in a link for that. So here are the steps. So first, we write the import statements, and then we just configure the bias detection. We load the dataset and split in train and test. We compute the fairness metric on the training dataset. Then we mitigate bias by transforming the original dataset. Then we compute fairness again in the transform dataset. Here we're assuming that you know this dataset, but of course this may not be the case, and that's why we have also included a link to some other example of exploratory data analysis on this dataset, so that you know a little bit more about the variables that are used and the relationship between this. For this you can do if you want to really dive deep into the details of this dataset. But for the moment, you can just assume you understand the dataset and you just want to optimize for the H variable. We run the import statements, and we're importing the German dataset. We're also importing the binary label dataset metric, which is used for binary classification problems. And we're importing this rewiring method. That is the one that we're going to use. Here we have an information. It's a preprocessing technique that weights the examples in each group, in each combination differently to ensure fairness before classification. You get the article that people is citing. So this is how you load the dataset. We have fixed the random seed also so that you get the same splits and you get also the same percentages of the fairness, of the same values of the metrics when we evaluate. So to instantiate the German dataset, you can just use the simple constructor, just German dataset and parentheses. But if you know already which protected attributes you want to use, you can define it right away. And we know it's H. And as such as the H is encoded in the dataset is number. And we want to really change the encoding of H into a binary variable because we're doing a binary classification. We are dividing, the protected and unprivileged and privileged groups. And that's how we do it by using this lambda function. You can also choose some categories to drop to some features, columns, sorry. And at the moment, we're not going to focus on these ones. We run the cell, and we also create a split, dividing by 70% of the data into the train test in the trained data set and 30% into the test set. Furthermore, we're going to need mapping for the privileged groups and the unprivileged groups when we use the rewiring algorithm. So that's why we define this one. To compute the fairness metrics, we're going to use the mean difference, which is an alias of, it's also called a statistical parity difference. This is the metric that Josephine was just discussing in the lecture. And if you forgot the definition again, you can click on this and you will get that. Okay, what is this? Oh, this is the probability that you get a positive outcome given that you are in the privileged class, minus the probability that you get a positive outcome when you are in the privileged class. So you're going to measure what is the difference between being in each group when getting positive outcomes. And the way you do this, you use this binary label dataset metric, where you give in the trained dataset and the unprivileged groups and the privileged groups. We run it, and then we see that we get a difference for around minus almost 13%, right? Since the difference is the unprivileged minus the privileged, we see that this is a bias towards the privileged group. Like they are getting 30% more positive outcomes than the unprivileged ones. And this seems quite significant. So how do you fix this? If you want to know about the method we're going to use, you can click on this link and you will get to the article. So to use this rewiring technique, what we're going to do is configure the rewiring algorithm, and then just fit the transformation into the trained dataset to get a new training dataset, which is a transform one. And now we can just see how this algorithm did, because we measure again, given this metric. And then we see that we have now a difference of 0. So the algorithm rebalanced the dataset in a good way. We added some exercises and questions. This is not in the original notebook. And this is just mainly because we want you to work harder and understand a little bit more of these techniques. So one of the exercises, the first one, is to change the dataset, for example, to use the adult dataset, which is also this is an income dataset. How we try to predict if people earn more than 50K or not. And then you can think about which protected variable you're going to use. So you can click here, and then you get to the documentation of the dataset. As a hint, there is another library, another notebook that we can see the use of the adult dataset if you're unsure on how to put things together, if you didn't manage to do it from the documentation. The second exercise goes for, let's say that I want to change my metric to disparate impact. I'm missing an E here. Okay, instead of mean difference. So hopefully this first introduction notebook will give you a little taste of what does it mean to work with these fairness algorithms. Of course, there are lots of other techniques that you can do, like in processing. And this is the second example that we have, where we use a technique called algorithmic adversarial debiasing, sorry. But to see the full use of this technique of rewiring, there is another notebook here that we haven't converted to Colab yet, but this goes through the whole process of doing training, rewiring, doing creating a model, rewiring again, and checking that this works. It's a nice overview. If you didn't manage to get the solutions, we provide also yourself. We provide a template or a cheat sheet so that you can try yourself also what we wanted you to test. And if you want to import, for example, the adult data set, just run this line. When you import the adult data set, you're gonna see a warning like missing data and some 3,620 rows removed from the data set. This is because this data set uses the standard data set implementation where they have some pre-processing where columns with missing values, for example, they are removed from the data set. So you can see more in this link on what kind of pre-processing is being done. From the link to the notebook that we gave you before, this is a programmatic way to get information about the sensitive attributes. We have the adult data set, we have the trained data set, and then we can just query it and ask it, what are your protected attributes, right? And then we see that this data set has race and sex. Okay, I can choose the first one, and then just define my privilege groups by taking the first one also, and then that's race. And the privilege group is race with a value of 1, and then privilege group is race for a value of 0. And this is, I think, white versus non-white people. So then we can do the same thing that we did before, using the same binary level data set metric, but now on this new data set, and calculate again the mean difference. And then we see that we get about 11% more favorable outcomes for the privileged groups than for the unprivileged ones, because this is negative, remember? So we can reduce the bias again by using the same technique, and we check again. And now we see that we get 0, which is nice. Now, if you want to change your metric, it's really easy. You can see that this implementation of the documentation of the binary label data metric, it has these metrics implemented. You can, for example, see what kind of metrics it has, and disparate impact is one of them. So you can click on it, and then you get the definition again if you forgot about it. And then you can just change to that, and then just run it. And I think Colab has now autocomplete, so you should just write a little bit here. It will autocomplete the right data set. That concludes our summary of the first notebook. Okay, I'll just go again to show you the GitHub repo again, because we have the notebook number 2 is a full end-to-end example for training the model and doing an in-processing algorithm to learn a fair classifier. This requires TensorFlow 1.0, so you can try it yourself. And the third one is a full example for in healthcare, and it's also a very long notebook. So this will take you some time to finish. But now I will go back to the presentation. Yes. So Josephine, would you like to conclude a little bit with the takeaways from today's workshop?
Yes, I will. And thank you to everyone who have followed along so far. During this time, we have looked into both some of the theoretical foundations of what it means to work with fairness in machine learning, and followed by some hands-on experience on how to evaluate and mitigate bias in a real machine learning pipeline. So we hope you have learned a lot from this, but to some it might have been a little bit of information overload. So let me try to sum up a little bit of the main takeaways. First of all, I think it's important to understand that defining what is fair is a difficult task, not always because it's a mathematically difficult task, but because what is fair is actually a normative question, and it depends always on the context. Second, transparency and interpretability are, of course, very important in their own specters, but it's also important with relation to fairness, as it can help us to better evaluate and understand if our models are fair or not. And finally, there's a lot of best practices now starting to emerge with softwares to support them. So we have looked at this AIF 360 today, but we also gave you a great overview of 2 other packages that are available that might be useful for you to start working on. If you want to have a bit more information about some of these definitions and what it means to be fair, then this Fair ML book, it's an ebook that we can very much recommend. It's under development still, I think, but it has some very good chapters on all of the things that we have discussed today, some of the metrics and how to understand them. And then also we recommend the AIF 360 intro by IBM, which is a PowerPoint presentation with some of the same things that we have discussed today, but in some different words and some different slides. So that might be useful as well.
And if you are really hardcore and really want to dive into this fairness in machine learning, we have also collected some links from what we have said during the whole presentation that you can check on if you have time. And with that, we want to thank you for being along with us during this workshop. Here's the link to our LinkedIn profiles. If you want to reach out and take contact with us, we will gladly talk more about fairness with you. And we're going to still be available for the rest of the time at the chat channel, answering questions if you have.
Yes. Thank you very much. That was everything we had for you today.
Bye-bye.